Welcome to the world of geometrifying trigonometry. It is also called the geometrization of trigonometry. Mainly, today we will discuss with the Gtsimplexes versus locked sets in geometrifying trigonometry. But before talking about the Gtsimplexes and locked sets, we should talk about the free body diagrams and the pictures of bridges or trusses, where we see several line segments are involved, and these line segments are considered as the beams placed on a floor plan. And whenever these beams are there are the triangulation kind of things, and these triangulations are like this, and we break the whole polygons into pieces of triangles. And when we break this kind of problem into triangulation, then it is the glued triangle. And when the glued triangles are taken into consideration, then the force travels from one line segment to another, and then it is carried to the another line segment. In this way, the Gtsimplexes are formed. And when the Gtsimplexes are formed, these Gtsimplexes can have multiple copies, and when these Gtsimplexes are placed one after another with other Gtsimplexes, then sometimes some line segments are collinear or almost collinear. And when these are placed like these, and then we see the Gtsimplexes gathered together to form the locked set. These are the simplest formulation to talk about the locked sets. So now it is forming a locked set. Okay, we will start with the simple line segment first. Suppose this one is a given line segment, and it is taken as the red line to identify that it is the initial line segment for the whole show. Now suppose the line segment is there. This line segment has a starting point and ending point, but if we rotate it by 180 degree about the center, or this, if we take the midpoint snap, then we can rotate it 180 degree, and the start point and end point are shuffled. So this is the line segment, and you cannot visually check either its start point is on this side or the start point is taken to this side. So line segment is considered as the two vectors disguised, that is, two hidden vectors are present. One vector is like this, where it is having a direction on this side, and another line segment is like this, whose direction is taken as a 180 degree rotated, or rotated with the 180 degree. Suppose we have selected it and snapped it to the midpoint. Suppose we want to rotate this whole thing. Rotate. We are using NanoCAD, where its behavior is little different than the AutoCAD. NanoCAD is free, and it has the API to demonstrate many things, so we can take it. Now we have seen it, its journey is on the left side, and if we want to take the journey on the right side, suppose you are sitting on a train and your seat is on the left side forward, you are looking towards the front side, then it is like this. And if you are sitting on the right side of the train along the journey, then it is the mirror object, and you can take it like this, where here's the then the journey is reversed, where you are seeing, look through the right side window. Now the journey objects, there are 4 types of journey objects. Suppose on the right side vector you have the 2 journey objects, and on the left side vector there are another 2 journey objects. So for every line segment we can have 2 vectors, 2 possibility of symmetry, and 4 journey symmetry are possible. Now suppose the line segment, initial line segment is given L. In this blog I have described the whole detail of the thing, that is the Sanjoy Nath'S Geometrifying Trigonometry.blogspot.com. You will get this picture also, where I have mentioned the differences between the Geometrifying Trigonometry Gtsimplex objects and Geometrifying Trigonometry locked set objects. You can get the tabular form with the 21 points. I am adding 50 more points. I am testing with the several conditions of journey objects before writing some interesting theorem on those things. Until validation are done, I cannot say those things properly. So I am working on those things. Now suppose this line segment is given, and on these line segments we are taking the output line segment. Suppose this is the input line segment, L is the universal input line segments. Now we can draw any triangle on this, where we can consider the output as, suppose, a green line, and suppose we are taking the complement line segment as a blue line, so that we can detect everything very easily. This is a convention that I can show you. Now if we make several copies of this similar triangle, suppose I have made similar copies, we can take the dissimilar copies also. Suppose we have stretched this point and make it dissimilar kind of object. Now see, if this line segment is taken, this triangle is taken, where the output line segment of the first triangle is glued with the input line segment of the second triangle. Suppose we will try to make these as a blocks so that we can demonstrate it better. Suppose we are making it as a block, BLOCK block, because making the block gives us the sense of locked sets. And first triangle block, this is a Gtsimplex, or it is a lock set also. It's the most fundamental lock set. Now when we take its multiple copy, suppose we have taken its multiple copy, then we can glue these triangles. We can make the block of this second triangle also. We can take the block of this second triangle also. This is a second triangle, and if we take the second triangle here as a block, and suppose this is a pivot point taken like this. Now with these copies we can do the multiplication. How can we do the multiplication? Suppose the input line segment of the second triangle is aligned and scaled to fit. There is a well-known engineering command, align, and if we align this whole block, okay, then it will ask the first point and the destination first point, the second point of the source to the destination of the second point of the source. These are shown, and third point is not taken since we are taking it as a 2D. Now it is asking scale the objects based on the alignment points. If we don't scale the objects, if we simply align them, then the things will not get scaled. So you will find the things like this. Now if we align with scale to fit, this is the interesting subject where mathematicians normally cannot understand, because this is the engineering term, properly engineering term from mechanical engineering and civil engineering, where align and scale to fit is a very well-known term, and which is the multiplication as per engineering heuristics. So geometrifying trigonometry starts with the concept of engineering heuristics directly applied to the mathematics, and canonical formalization is made on the mathematics through the engineering heuristics. So the subject is straightforward, initiated from the engineering application. So there is no way that the subject is a pure theory. No, the subject's fundamental theory is the free body diagram. Then it came to the geometry design due to bridge designing, or for architectural engineering, or for building designing, or for urban planning, or for jewelry designing, or in the fashion industry, wherever this align and scale to fit is a very common term which mathematics world don't bother too much, because this special kind of engineering heuristics on the CAD world is not so much well aware in the mathematics world. But we want to introduce this to the mathematics world because it has a huge potential to play with the practical problems in structural engineering, for mechanical engineering, linkage mechanism designs like this. Now it is asking the scale the objects based on the alignment points. Yes, now it is the aligned and scale to fit done here. When the align and scale to fit done here, the triangle objects are preserving their own input line segment and the output line segments, but they are simply aligned and scale to fit. We can do 4 symmetries while we do these kind of things. I am trying to show the 4 symmetries here. Suppose I am making 4 copies of the same object which is formed due to gluing. Here we will keep it intact, that is the symmetry 1. Then we will do the mirroring of this with respect to the input line segment of this. When mirroring, it is asking erase the source object. Yes, I will not keep it because 1 copy is already kept. Now we want to do the mirroring of this object which I have kept intact here, which is mirroring or which is just rotating of these things. Suppose we want to draw a perpendicular on this line segment. The best way to draw perpendicular on CAD here is we can set the UCS, user coordinate system, to this line, and when this line is the user coordinate system, now we can easily draw a line segment to the midpoint of this, and that is the mirror line. If we take the snap and if we take the ortho, then the orthographic line is drawn here, and this is the mirror line of this constructed line segment. If we do the mirror, now mirror is the affine operation, so the coordinate system is immaterial for that, and I will erase this. So the mirror line is this one, and now one symmetry is formed in this way. So 3 options are prepared. Obviously 3 options are prepared. Now we can back to the UCS world, which was the natural coordinate system. Now we can make a copy of this. We can make this copy here, and then we can do the mirroring about this line segment, and we will again erase this. So these 4 symmetries are made. We have seen that when we are gluing due to multiplication, then due to align and scale to fit, we are getting a picture like this. So when we say that we have to construct all possible geometries, then we have to copy the source object also into 4 options. We have to copy these into 4 options such that we can consume the 4 outputs. To consume 4 outputs, we have taken it in this way. First output is generated. This is one Gtsimplex. This is a valid symmetry. Second output is taken, which is also a valid symmetry, and here we can take it, we will move it to here. Then this is also a valid symmetry. We can take this red line to here. The red line and blue line had to interact. Here the red line and blue line had to interact, and so all these 4 symmetries are the valid output Gtsimplexes forming due to the multiplication, and we can keep these things beautifully aligned here. All these 4 options are the valid options. Now what are the input line segments and what are the output line segments? I want to show you that, suppose taking it here, I will take its height as 40, and suppose I am taking its height as 6, then it will come into the proper scale. Now if we take it as the input, if we take it as the L as the initial line segment, and it is the input line segment for every cases. This is the input line segment for every cases. This is the input line segment for every Gtsimplex is so formed. Now what is the final output line segment? When we are multiplying these and when we are doing the align and scale to fit operations, then this line segment is the initial line segment, which is giving the output line segment is blue one. If we take it, and if we take the output line segment as the green one, then our alignment has to do in this side. If we take this as the output, blue line as the output line segment, then we have shown the alignment. Now for this triangle there is also an output line segment. If we take the red to blue is the output mechanism, then red to blue, again red to blue, which gives this blue line as the final output line segment. So if we take the rule, the convention that red to blue is the mapping of the input to output, then red to blue is followed here also, then this blue line segment is the final output line segment for the symmetry 1. And for the symmetry 2, one interesting thing is happening here. You cannot see the blue line properly because that was overlapped on the red line, and that blue line is the output line segment. Here after selecting, you can see this is the output line segment of the second symmetry. In the third symmetry, this blue line is going here, and it is the output line segment. So the length of all these blue lines in the output line segments are same every time, but the positions are very different. In the fourth symmetry, you can see the blue line is here, which is not same as that of the others, and so for every different cases these blue lines are going in the different positions. Suppose now we want to show you that if the four symmetries are taken and all these outputs are now generated, and now if we want to glue this triangle with the output line segment blue line here, suppose here, then again I have to draw four symmetries for this option. For every of these we have to draw four symmetries. Suppose on the second multiplication I have to take the four symmetries for each of these, and on all the output line segments I have to glue these, but I am showing here only one. I have made a software, and that you can find freely in Autodesk forum in name of automated trigonometry, where you can play with multiple varieties of symmetries. All the symmetries are valid, and I challenge you that trigonometry, the classical trigonometry, also want to say the same kind of thing, that the outputs have four different symmetries and all these four output symmetries are valid. All plus minus into divide have the same kind of options. Now for simplicity I am trying to show you one example of the gluing with another triangle. That is also valid, because the gluing of another different triangle is also necessary to demonstrate you. Suppose here the red line is the input line segment and green line is the red line and the blue line is the output line segment. Suppose we have taken the convention here, and at every stage this convention can change. So ABCD means cos theta, EFGH means sin theta, IJKM means tan theta, where in the previous videos I have already shown that what to take as the input line segment and what to take as the output line segment. The conventions changes when we consider different kind of line segment trigonometry ratios, or when we consider different kind of 12 symmetries of every numbers, then we can see this kind of gluing things happens, and the input output conventions changes as per the necessity of the operator charging. Multiplying with any trigonometry expression, or adding any trigonometry things, or adding any number, or multiplying any number, dividing any number, plus minus into divide, whatever we do, that is ultimately an operation charging on the previous data and previous line segment or previous geometry, such that we can get a new geometry or augmented geometry. Let's see the augmentation of new triangle due to the multiplication here. Again we will do align operation, and that is the align and scale to fit. Suppose we are taking this as the input and we are gluing it with this point of the final output. Now we are gluing it with this as the final output. Since we are doing in the 3D, we are not taking the third point. So I have just pressed enter and we are just scaling it. So now the output line segment has gone here, and this whole thing is now forming a Gtsimplex. Now if we take the simple case here, suppose this is a Gtsimplex and this Gtsimplex is added with another Gtsimplex here, that means it has the output line segment blue and the common line segment L, and that is present there also, and that L is present here also. Now if we want to put the edges of the end point of one line segment, output line segment, with that of the other output line segment, then the whole thing is forming like this, and now the two output line segments are placed here. And if we place these outputs again, then we can take it again and we can make another copy of this, and then we can take the additional output line segment here and it is placed on the, we can place it on this output line segment's endpoint. Then the whole thing is forming a locked set. So whole thing is a locked set. We cannot say that any single thing is a locked set. These kind of behaviors are found in the locked sets, and we can add many other things to these locked sets, and every of these operations have a significant meaning. Significant meaning is there to the geometrifying trigonometry, because in theory of geometrifying trigonometry this addition process is described as the four symmetries. Like we could place it like this, instead of this endpoint we could place it like this. We could take the mirror image of this and we could place it like this, then the line segments would get the different arrangement. But the valid flow of the force or the valid flow of the of anything along these output line segments is same conventionally as per the theory of trigonometry. The total length so formed is same because we are adding the outputs with the other outputs, and then we are adding another output. So ultimately the outputs are added, the inputs are not added. So as per trigonometric conventions, it can take any shape, but it is better if the things are collinear. Suppose in this case we have seen that the output line segments were collinear, the two blue lines were collinear, so it is naturally summable. So I think you could understand what is the Gtsimplex, where only multiplications are involved, and when addition or subtractions are involved, when the reverse direction line segment is placed end to end, then it is the subtraction. In that way we can consider that the addition in one symmetry can consider as the subtraction in another symmetry, but the whole story changes because different symmetry is not only about the output line segments. Every symmetry also carry with it all the involved line segments which are involved in its own lock set, or whichever line segments are already involving into its valid symmetry or in the Gtsimplex. So all of these line segments are forming a conglomeration, and within this conglomeration we can have several theorems like circle with the 3 points. Suppose if we are taking a circle with the 3 point, now after forming this kind of Gtsimplexes, and we can see that if we take the 3 points here, and then this point is also involving into the same circle, and you can see that this point also comes under same circle. So these are the special kind of theorems we can get, the isocyclic points which are forming in the Gtsimplexes. And if we, for different values of this theta, the behavior of these calculations can have the different theorems and different properties. And these theorems were never discussed in classical trigonometry because In classical trigonometry, we were not constructing Gtsimplex. In classical trigonometry, we were not constructing locked sets. So we could not have these kind of theorems ever possible in our classical trigonometry. The point of intersections of different line segments can also have very unique invariant properties, and which were never discussed in trigonometry subject, and those are all valid point of discussion due to manufacturability, due to the linkage mechanisms, due to robot arm movements and automated guided cars movements, or in the potent folding mechanisms. In these kind of cases, or mainly in the structural engineering, the bridge designs, or in the architectural planning for the space planning, these kind of theorems are very helpful, because if we can tackle the things with the theorems, then we don't have to handle lots of iterations. The main purpose of theorem is to reduce our iterative hard works. Now I should explain simply some points on the differences between the geometrifying trigonometry's Gtsimplex objects and geometrifying trigonometry locked set objects. On the left side, the Gtsimplex objects are discussed. On the right side, the locked set objects are discussed. The point number 1 says that affine point objects are null Gtsimplexes. That is, the point objects. The affine point objects are not the main objects of geometrifying trigonometry. Point objects are helpful for theorem designing. Point objects are helpful for gluing in the locked sets, but those are not very important things in Gtsimplex construction. Affine point objects are null GT locked objects. In locked set cases also, these point objects are not discussed too much. When we discuss about the line segments, and circles are also not discussed too much. The circles are important for the theorem designing, but in construction protocol, the mirroring, align to scale, align scale to fit, align and not scale to fit, scaling, rotation, these are involved. Triangle construction, triangle gluing, constructing of multiple polygons with triangle gluing. In the previous videos, we have already shown that how to describe a polygon of any kind of shape with the triangle gluing mechanisms and triangle construction mechanisms. Triangulation in the Voronoi way, or the triangle construction in Mandelbrot sets, or triangle constructions, the new point additions in fractals, are not same as the triangle construction in Gtsimplexes or the triangle construction in the locked sets for the geometrifying trigonometry, because the purpose of geometrifying trigonometry is to express any trigonometry expression in a geometric form like these, which I have demonstrated here again. And in this kind of geometric form, we can describe many more hidden understandings, many hidden insights are there. When we draw the pictures, then we can visualize those things, then we can find the polygons, we can find the elliptic curves, or we can find the circles or cubics which are passing through some special points on these triangulated objects. Those are the point of concerns in geometrifying trigonometry. Until we verify these kind of geometric shapes with multiple values of theta, suppose in the dynamic geometry, if we change this theta once, then the whole arrangement changes, keeping the same rule fixed. All the symmetries will dance together, and it is the best way to draw these things like this, because all the symmetries are constructed at the same line segment. So all the symmetries are to draw on the same place, on the same line segment L. That is the best way to draw the whole things. This is the actual construction of the first Gtsimplex, where all the L are kept in the same position. Now the points are there. In these kind of constructions, we can see the interesting properties, and here I want to show you a simple kind of theorem here, which is present like this, and here we can find a rectangle so forming. We can see that this point of intersection, if we draw the circle from this point, and if we take the 3-point circles or the radius here, then if we draw the circle here, then for some value of theta, it passes to the point of intersection. These kind of theorems are always there in geometrifying trigonometry, due to the fact that it is a it is the point of symmetry construction. If we draw the circle here with this point of intersection, that circle passes through this point also, if for some particular theta. This kind of theorems are also there, and from that we can generate different kind of identities and different kind of inequalities, which are very interesting for the force flow mechanisms and for the free body diagrams and optimized free body diagrams constructions for structural engineering or for linkage mechanisms. Now we are coming to the second point, affine line segment. Everything are affine here. Affine line segment objects are functional Gtsimplex objects, because the structural unit can have the points, can have the lines, can have the triangles, but the functional operations are done with the line segments only. The affine line segment objects are the null Gtsimplex GT locked set objects, because until the triangles are glued, we cannot take those things. But here the point I have to revise, because in some researches I have found that affine line segments are taking part in the locked set operations. So affine line segments are not null, actually they are involving in the operations. Affine line segments are not null objects for Gtsimplexes, not they are null in the locked set. Previously when I was not working with that much varieties of cases, then I had the consideration that they are null objects, but now after getting some counter examples, I have concluded that line segments are not null objects in locked sets. Triangles are very functional objects. Triangles are the structural objects and the functional objects for the geometrifying trigonometry. Obviously trigonometry deals with the triangles mainly, and line segments are important, mainly the input line segment and output line segment, and the relationship between the input line segment and output line segment. Suppose when we take cos theta, that means input line segment is hypotenuse and output line segment is base. If we take sin theta, then same input line segment is hypotenuse but output line segment is perpendicular. If we take tan theta, then the game changes. In that case, the input line segment is taken as the base, which is at the denominator, and perpendicular becomes the output line segment for the same triangle. So the game changer is which ratio we are taking and what kind of symmetry we are considering. Now every different symmetry has a different name. For cos theta there are the names of A, B, C, D. For sin theta there are the names like E, F, G, H, and the construction protocols are also involved. In my previous videos I have already shown that with the simulator and also with the CAD, also with the GeoGebra, so that you can understand these things. In the point number 3 we say that affine input line segment objects and the output line segment objects interact only as the overlaps in Gtsimplexes. Those overlaps are aligned and scaled to fit, and even after aligning and scaled to fit, you can cross verify through the moving of the alignment conditions, such that you can see that proper alignments are there. And but the thing is logically locked. Physically it is also locked, but in CAD you can obviously cross verify, but that is not the practice. The practice as per theory is that they will remain locked and they will behave as a theta, and until the theta value is changing, this whole locked set will not change. The thing will change the moment the theta value, the seed angles are changed from 0 to 360 degree. We will see the dancing of all these symmetries together. They are moving here and there and still following some invariants, and that is the interesting research on geometrifying trigonometry, to identify and to check the nature of the invariants when the seed angles change from 0 degree to 360 degree. For every small variations, the dynamics of these line segments of all the symmetries changes and prepares a beautiful pictures and beautiful fractal kind of things also when the multiplicative ratios are more and when the series is big. And in that case we have large set of line segments, and all the line segments are dynamically changing when theta are changing, and still some invariant properties are there. Suppose a circle is there and it is passing through certain points for every value of theta from 0 degree to 360 degree. That is a invariant property. Or sometimes it can happen that if 3 line segments are intersecting at every point, suppose this triangle so formed, suppose this is a triangle and this triangle is formed and it remains similar whatever the theta is changing, then it is also an invariant property. It can have many different kind of invariants, and those invariants were never discussed here, and you will get this picture in this blog, and from where you can get the detailed data. I am discussing it here again. In the point number 3 we have talked about this, and for the affine input line segment objects and the output line segment objects interact not only as the overlaps in the locked set, but they can also meet end to end. And in the locked set here, because Gtsimplex objects are also locked sets and locked sets are also locked sets, but all locked sets are not Gtsimplexes, but all Gtsimplexes are locked sets. That is in a point here, and I have discussed many such points here which I have already talked here, and I have already demonstrated the things that I have written here geometrically and in front of you with the CAD commands, such that you can understand the points that I have discussed here in the differences, so that these things can become very much clear to you. And these points are very important for the people who are learning geometrifying trigonometry for the first time, and obviously the school students who want to visualize the trigonometry expressions purely geometrically, and when the students want to verify the behavior of free body diagram, when the controller values like theta or the forces lengths are changing, the Siva's theorem can have the different impacts, the Lami's theorem can have different impacts, multiple triangles are taken together, and the property of these all bunch of line segments are a bigger subject than classical trigonometry, because in classical trigonometry we discuss about only one triangle or two triangle at a time, but in geometrifying trigonometry we take care on the school level problems of trigonometry with more detail and with all more symmetries considered at every step. And for every plus minus into divide we have 4 symmetries, so all the symmetries are constructed through the simulators, and then we try to address every line segments uniquely as per the construction protocols, and then we try to examine that which are the key properties which remain as the invariants, which are the key characteristics of these geometries and the positioning of line segments which remain invariant even theta is changing from 0 to 360. Some properties are still invariant in the whole set of the constructed line segments. That is a very interesting bigger domain than classical trigonometry, and in this video we have started demonstrating the differences between Gtsimplexes and locked sets, and in our next videos also some of the cases will be discussed to examine the things in more depth, such that you can think about more deep theorems that you can design with geometrifying trigonometry. We will discuss several properties that we have found by running the simulators for near around 10 years to 15 years, and previously there was no simulator, I had to make it, but before that I used to construct these things in CAD with the Lisp or with VBA or manually, that I have shown in front of you here, such that I could find many invariants, and to do that I had to construct many triangles. But now with the simulator I can play with it very easily, and I can see many invariants very easily. You can also see many invariants when you will do the data science handling on millions of line segments constructed through this process, and that will give you a deeper insights. And it can happen that someday we will find some theorem with which we can control the protein folding mechanisms, or with which we can control nanorobots very easily, because the geometric theorems are invariants in the micro scale also, and those theorems are invariants in the macro scale also. And because it is a pure logic and the pure reasoning, and the reasoning don't change when we are working anywhere, so it is mainly affine geometry. The conditional cases are not there. Some facts are true for any kind of conditions, and for that reason the theorems are very important, and mathematical theorems are more powerful than many other theorems, because those theorems work for high energy physics also, those basic theorems work for the low energy physics also, the basic theories work for space-time cases also, and basic theories work for the cases where space is differently taken with the time, then in that case also the fundamental geometry conditions are valid for the definitions and the sense of fundamental mathematical theorems are valid for the quantum systems also, and they are valid for the non-quantum systems also, like in the classical mechanics also they are same. So when we get the platform to do reasoning on the symmetries, with the four symmetries, and when we can do reasoning with the pure geometry on the affine spaces, that has a power that the theorems designed on those cases work for any kind of systems, and so it becomes pervasive. And we will discuss with those kind of invariants that I could found with my experiments, and I want to listen from you also, so that you can also come up with the more number of theorems, and which are very interesting and applicable for many engineering purposes. And this subject started with the engineering heuristics, so obviously whatever the theorems come in this subject will have some scope, and will always have some product design in several engineering fields. So obviously this is a very interesting subject where the practicality is the fundamental basis. It is not the theory which will have to find the practical basis someday. It is not the case for this theory, because this theory started with the practical problems of mechanical engineering. This theory started with the practical problems of the structural and the civil engineering. So it is very pervasive in the engineering fields, and non-engineers had the problem that they are not well aware with the operations like align and scale to fit. They are not always very comfortable with the terms like blocks. The non-engineering peoples are not always comfortable with several mathematical things which engineers use specially, but mathematicians don't use in their common working. For that reason, some gap is always there, and for that reason mathematicians sometimes don't consider geometrifying trigonometry as their cup of tea, but engineers are always very happy with geometrifying trigonometry more than classical trigonometry. And programmers are also very much interested with geometrifying trigonometry, because for the programming in the computer graphics systems, they can use the theorems directly to optimize the algorithms with much faster level. And that algorithm which use the theorems, they don't have to play with large chunk of data, because the theorem works with the small chunk of data also, and that works for large chunk of data also. So when you have the theorems at your hand, then you don't have to put load on the processors, you don't have to put load on the databases, because if 3 plus 3 is equal to 6, then it will valid for the small data cases also, and that will work for the large data cases also. So it helps us to reduce the complexity of any programming system also. So geometrifying trigonometry is really started with the applicability kept in mind, and it is not a theory for just theoretical purpose. It is not that theory. It is very interesting because it exposes the geometry of classical trigonometry. Not only that, it exposes all possible valid symmetries for every single trigonometry expressions, and then it searches the properties and characteristics and deeper insights which are present as the invariant forms or variant forms or inequality forms or similarity forms inside those geometries. That is the interesting part. In today's video we have explained the constructions of Gtsimplexes, the constructions of locked sets, and the schematic differences between the Gtsimplexes and locked sets. And I think after seeing these constructions, it is now clear to you how to think about Gtsimplexes and how to think about the locked sets. Thank you.